Good morning. Good morning, good afternoon, good evening, everyone. My name is Kei Yoshimura in University of Tokyo, Japan. And I'm really happy to have a keynote speech in this nice, wonderful workshop. And also, I also like to thank Harold and the organizing members to hold organize this wonderful workshop. It was, indeed really, well, once in 2 years probably to make a presentation in front of international audience. It's still remotely, but in a presentation style, not in the monitors. Well, today I'm going to talk on this title. Actually, this one was proposed by Harold, but I really liked this title, so I steal this title. Advances in water isotope observation, simulation, and model data integrations. And the contents of that presentation is actually recently published by 2 papers written by Tada et al. And Toride et al. And also some of my works has been going to be referred. So let's move on. So I just want to start from very how can I say, nostalgic studies too, similar to HC. But all of us are familiar with isotopes. But our water isotopes are used for different purpose. And then sometimes it is going to be problematic or the source of the miscommunications somehow. Well, so I'm going to list some of the examples. So, it is most popular, I guess, people who use isotopes as a temperature. So it's Antarctic ice cores delta D. And then this is also always, almost directly converted into temperature. And then there is some uncertainty, of course, so there is studies. And then some people uses isotopes as a rain amount. And then this is a study also a little bit old, but speleothem in China. And then this is O18 from calcite. So that then we translate this information into rainfall activity or the intensity of the summer monsoon. And then we use this information as a civilization or something like this. Other people uses isotopes as a moisture circulation proxy. For example, this is a Zhongfang Liu's study, but using 2 pair of the speleothem or lake sediments, O18, then it can be used as a proxy of PNA signals. So actually, this is regarded by similar as a moisture circulation proxy. I'm not going to go in detail. And then other people, this is work done by my former student, Song Wei. He used isotopes, or there are people who use this isotope as a indication of transpiration. Actually, this study was how can I say, motivated by the work by Scott Josesco. It was interesting innovation afterwards. Anyway, so there are lots of different way of the translations. However, the answer is all true, but actually all wrong. Means sometimes it is wrong, true, but sometimes it is wrong. And then, but what is really trustable is fractionation. So fractionation is only a physical and chemical property of water isotope. And then, of course, I'm not going to go in detail, but this was well known and well measured. So, and then the fractionation is the source of the old apparent relationship. Well, then what is implemented in the models? Actually, it's not that simple, but there is a different fractionation like equilibrium and the kinetic fractionations. But if we can assume that we also know kinetic fractionation very well, which isn't so true, but still methodologically, we have some robust way to implement those fractionation processes. So what we usually do for also Camille and the other climate modelers, we implement those fractionation processes in the models. And then incorporate water isotopes fractionation as water isotope as passive tracers. And those whenever phase changes occur, those fractionation process or the isotopic water behave differently to the ordinary water is implemented. So what usually we do is we need to take a look on the cause where phase changes occurs, and then it is related to the wet process, like a precipitation process or condensation processes. Well, knowing this, so how can we use this model, isotope GCM, isotope RCMs, or isotope ESMs? So it can be summarized as this schematic. So so the left-hand side, we have a delta 18, which can be measured. And then on the right-hand side, we have a temperature of precipitation or something we want to know. And then conventionally, we make some sort of empirical relationship between isotopes and temperature, precipitation, climate informations, or weather informations. So kind of simple regression analysis is made. However, by using isotopic model or forward proxy model, I mean, it doesn't have to be GCMs, but somehow it is implemented. I mean, physics is implemented. It is called forward proxy modeling. And then this proxy and climate or proxy and weather relationship may vary in space and time. So that by using the tool or the forward proxy modeling, we can understand why temperature is has a good relationship with isotopes. And then sometimes we can generalize this relationship, or we can tell it isn't true to interpret as a single regression, or it should be made by multiple regressions and so on. However, it is actually opposite side. So we need to know temperature and precipitation to understand what is mechanism in delta 18 or the isotopes. But what we really want to know is the other right-hand side. So we need to go further, and then which is today's topic, data assimilation. And then using proxy as a constraint to the model, I mean, for the proxy models, and analyze a consistent or comprehensive climate weather systematics is the way we, I mean, actually I'm going to, and my group is doing. Well, then what is data assimilation? It's a very, very cartoon, but it is my understanding, actually. It is like this level, but what we have to have is two different way of estimation. One is observation, one is model simulation. And then if we observe something like delta 18 or vapor, then observation has this range. I mean, there should be some uncertainties. So there, the range is very important. And then the simulation also estimates somehow with different range and the different mean. And then actually what is true is there should be somewhere truth. Means in between or in some outlier. I mean, we don't know, but there should be some truth. But which is data assimilation. So we want to mix those two informations to estimate the truth. In this case, data assimilation actually is going to be in between those two estimates, and the important thing is the uncertainty would be smaller than each of them. Well, but mathematically, which it is going to be a little bit complicated. This is basic form of data assimilation. In this case, yeah, and then actually in this case, something called online data assimilation. So in this case, the model is M. So the prognostic or initial condition of temperature, precipitation, whatever, with the isotopes are going to be included in the X, the matrix. And the next time steps state is going to be estimated by the model. And then most important equation is the third one, which is so-called common gain. And then it's actually the weighted mean. So the weight is represented as a K, and Y is observation in this case. And so the K is like a mixer. And then in most of the case, even though we do have a gridded information for all the variables in the model, but it's not the same as what is observed by Y. So in that case, we need to have something called observation operator, H, to convert the gridded information to the where do you have observation or time you observe. Then direct comparison can be made by Y minus HX. So that this K, a weighted mean, is going to be used to analyze the final analysis of each variables, like temperature or those kind of things. So the message here is those modeled variable expressed as X, not only isotope delta, but temperature and the precipitation or humidity or wind fields. Those are also constrained by this Y, which can be isotope or meteorological fields or whatever. So once it can be make a direct comparison between the modeled variable and the observation, all the variables in the X can be influenced. Okay, so I'm going to move on to the observation part. So as HC and other people introduced yesterday, we have a lot of new instruments, and then new observation emerged. And then one of my favorite is water vapor isotope measurements. I mean spectroscopic or laser mass spectrometer. And especially these Picaro instruments, I used it over party fields, and then it can observe, measure the isotope ratio of vapor once in 1 second, 1 hertz, which is very different from what I've started. When I started, it was a cryogenic method was popular, so that I needed to stay at the site overnight for like more than hours to obtain 1 milliliter of ice. Well, but by using this, actually it changed the game. And also other instruments, I mean, seems as it's a spectroscopic, but satellite measurements also became popular. And then ERZ on METOP, introduced by Matthias yesterday. It observes the mid-tropospheric delta D, and then it also can observe, make measurements for global daily snapshots, which surprised me a lot when I first saw. but which actually automatically triggered the data assimilation exercise. Well, so I tried data assimilation because we have two methods of estimates. One is from the model, one is from the remote sensing, the measurements. And then apply the LETKF, local ensemble transform Kalman filter, to get the analysis of water vapor isotopes. And at that time, 2014, the target was where or whether the isotopic information could have an influence to the other meteorological variables. And actually, it was turned out that true, that this figure is telling the time series of temperature for near Tokyo, and it was an idealized simulation. So we knew the truth. So black is truth, and green is the assimilated. And then the top one is no assimilation. So actually there is a big discrepancy between black and green. And bottom is whether when you have, I believe it was GNIP observation was used. So at that time, it's not the precipitation, but I assume that there is a vapor isotope measurements at that old GNIP sites. So black and greens are quite similar to each other, which means that by telling the isotopic information, isotope measurements to the model, it can have a potential to correct temperature or other meteorological fields. Well, and it was 2014, so time passed, and then we thought it should be studied more. How did the isotope work really work? So Kinya Toride, who is in Washington University right now, he investigated similar experiments, but using a conventional meteorological measurement network known as PREP buffer. And in addition to PREP buffer, we use ERC measurements. So as I showed before, ERC delta D is has a highest sensitivity at 4.2 kilometer mid-troposphere. And then actually it has a much finer resolution than the model I used, which is T62, which is about 200 kilometer in 1 grid. So we averaged those observation measurements within a grid to make something called super observation to reduce the measurements error. And then in total, the observation number is compared to the conventional PREP buffer observation, which is it is 2.1% of the data observation number data added. So which isn't that much. So, okay, so the results. From now on, I'm going to show some maps, and then the impacts is shown by red and blue. And the red color here is improvements by having isotopic information. And so delta D is shown in the left-hand side figure, and there is an impact over the east side of Pacific. Actually, it is because the highest impacts, highest improvement was made over those areas because of the relatively less observation was available at that area at that time. So it's not that always true to have a biggest impacts here. But there is a overall reddish color is shown. It means that the improvement is, there is a positive impact by having ERZ data as a data assimilation. And as shown in 2014 paper 2, there was a positive impacts for other meteorological quantities like zonal winds and precipitation. And then this figure in the bottom is showing the zonal zonal circulation over this area at the rectangle here. So this is Walker circulation. And then there is two cells here and there with this direction and then that direction. Sorry to explain poorly, but this figure is showing the scale improvements by latent heat profiles. So apparent improvement on the center or the uplifting part of circulations. The red color is showing improvements in latent heat profile. And then the relatively less improvements in the subsidizing area, which is actually reasonable to because the isotope has a good reflection to the phase change. So the uplifting part, there is should be a lot of phase change of the making the precipitation and almost no phase change over the subsidizing area. So that there is a big impact, good impacts in the latent heat profile over the uplifting parts. So we investigated how this isotopic information was influenced to the meteorological variables. We separate into two. One is dynamical information, and the other is thermodynamical information, which is dynamical means wind speeds, basically, and thermodynamical means temperature and humidity. And then in the data assimilation method, there is something called variable localization method. Variable localization method means that we can turn off or turn on the influence from the data assimilated fields. For example, in a normal way, we use all variable UVTQ and delta D influence to UVTQ delta D. So, but we can turn off the impacts. Data assimilated variable of isotopes is not going to influence T and Q in this case. But vice versa, T and Q influence to delta D. So actually, this figure is showing the impacts of dynamics because we turned off the impacts to temperature and humidity, and then vice versa for thermodynamics. So then by using this method of localization of variable, we can identify or we can quantify the impacts of each variable to the different fields. And the yellowish figure, these figures are the profile of the improvement in skills. So in total, 20% of delta D was improved or specific humidities at the highest improvement in the 600 hectopascals, which means reasonable, which is reasonable because of the data availability in IAZ. But if important message here is the both impacts are the highest, but more impacts to the thermodynamics rather than blues dynamics. So what isotopes can influence more is the temperature and humidity or thermodynamical fields, which is also reasonable because of the natural behavior of isotopes, which is fractionation. And then which is almost consistent to all the other variables too. And also there was a question that because delta D and the humidity has a very similar characteristic. For higher the humidity, higher the delta D. So what is the unique influence or unique benefits of delta D was also investigated by similar method. But in that case, ERC Q and delta D were assimilated simultaneously, or only humidity was assimilated, or delta D was isotope was assimilated. And then the important message here is almost the same, that for delta D, actually telling delta D is the straightforward and then having the biggest impact by yellowish color. But other quantities like specific humidity with zonal winds and the vertical velocities, in those cases, green is larger than yellow. Means humidity constrains the meteorological field better than delta D. But
now 3 minutes.
Okay, 3 minutes. Okay. So the impact actually, but still we have a shortcoming. So we actually in those studies still idealized information was used. So but there was a big gap between actual data is used and idealized experiment. So in this study by Tada et al., we first enabled to use actual ERZ data. So in that case, Jean-Lionel Lacour gave us actual measurements of ERZ delta D, and then we tried data assimilation using them. And then actually I was very nervous before I saw the results, but the results was okay, meaning that the improvement, in this case, blue is improvements here, but root mean square error of delta D was decreased nicely, consistently. And then the impacts to the other variables, specific humidity, temperature, zonal winds, those quantities are not that good as idealized experiments, but blue is good, and then blue is larger than red. And then we investigated what was the impacts in the synoptic scale events. So actually by having isotopic information, actually the weather was nicely analyzed. So the trough was analyzed here, and then the data assimilated fields, and circulation associated with the trough was somehow simulated, and the precipitation fields associated with low pressures was also analyzed too. And then actually, because of the improvement in the weather fields, so that the forecast from this initial condition was also improved. So we successfully showed that the isotopic information has a possibility to improve the meteorological forecasts. But summary and the way forward. So I showed that there was a positive impact of the isotopic observation by data assimilation. However, we were able to confirm the benefits. However, the improvement has not been yet been confirmed for the case where isotopic information is added to conventional meteorological observation. So the last experiment was without conventional meteorological observation, different from the Toride et al. So, but of course, that is actually our hope to do so. But so far, we haven't been able to do it. And then we know there's some reason here, but actually we have a very poor model of the performance over tropics. So this is just a performance compared with age observation, but the white color means no correlation between observation and simulation. So actually, even though we are trying to assimilate information from the measurements, which in those places, we will have almost no impacts. So we need to improve the model. And because I didn't tell anything about the paleoclimate reconstructions, but I just want to make a final remark on the paleoclimate fields. So data assimilation is even more popular for paleoclimate. And then the isotope has been used for paleoclimate data assimilation more and more recently. And then the online and the offline data assimilation is also an issue. And then whether we are going to use a reconstructed variable or measured variables is also an issue. But recently, the impressive paper was came out from Jessica Terrini and Osman, I mean, Terini's group. But the FGM data assimilation using ISO ESM and then isotopic data proxy is can be made. So this kind of data assimilation for paleoclimate is another direction for us too. And the offline data assimilation seems preferred, whereas online data assimilation is used for weather scale. So this is the final. Thank you very much for listening.